Hey everybody, happy May 19th, happy last week of the school year. Thank you so much for working so hard. Hopefully you're having a little bit of a dance party at home, celebrating as well. But I'm also excited to model some real world situations. We're looking at Ferris wheels today, but there's lots of different things you can model with trig functions. So just one book section today with a worksheet and multiple choice going on. We'll wrap up with Fluency Test 8 on Thursday this week. We'll try and get it posted early if you want to get a jump start on that, and hopefully have everything wrapped up this week. If you need to do something extra, I will probably reach out to you individually to set that up for Tuesday, May 26th. But otherwise, really thankful for it. Please try and stop into the office hours at 10 a.m. to 11 a.m. or 12 p.m. to 1 p.m. on either Tuesday and Thursday, at least just to say hello, say goodbye, so I can wish you to have a great summer, and just check in if you have any questions. So again, take care, and let's take a look at our lesson this week. So again, here are all the skills that'll be on FT8 that you'll want to make sure you look back over as you study and prepare. The newest one is to create and analyze trig models, which we'll be covering today. And then the word wall with all those big takeaways will be at the end of this video, and I'll try and make sure to post that as a PDF on Schoology as well ahead of FT8. Okay, so here we are on page 541. We're going to use these trig functions to model real world things, and we're going to identify key features of these functions. So you can pause, go ahead and read through the paragraph here that gives you all the important information you need about this particular Ferris wheel. And so go ahead and pause and read, and then I'll pick it up there with question one. Okay, now that you've read that, let's start to answer these questions not from a math standpoint, but just from a making sense standpoint. So what is the height of the car when it's at point A? So obviously our radius here, like we said, was 44 feet. So this is 44 plus whatever this gap is. So 100 total, so that makes this 12. So that must be at point A, that must be 56 feet above the ground. So that feels pretty good. And then what it's going to have us do on the next page is try and analyze this picture for all these different key points at A, B, C, and D. Okay, so I went ahead and re-pasted that picture here. So again, we have 44, 44, and 12. If we're kind of thinking about splitting this up. So 56 feet total for that point. And then we also know it makes one rotation, again in this direction, in 60 seconds. Okay, so again, just through common sense here, we're breaking this up into 4 sections. So really, it's about 15 seconds per quarter here. So we're going to look at D being in a height of 12 for point D. So Tyrell makes a table showing the height of the car in feet at various times. And so we're going to complete this table. So I double checked reading on the previous side. It said it wants us to start at point A. So what's the height of the car at point A at 0 seconds? So that height of point A, which we already found in our previous, was at 56 feet. 15 seconds later, it's going to be at point B here, right? It's going to be at point B. So that's at that full 100-foot height. Another 15 seconds later, so that'd be 30 seconds, it's going to be at point C. But at that point, it's back to 56 feet. And then at 45 seconds, it's down here at the bottom, so it's only 12 feet above the ground. And then at another 60 seconds, it'll be back at point A. So it's completed its full. So it went from point A to again at point A in 60 seconds. That'll be important later. So that's 56 feet. And then it just repeats over and over and over again, right? So another 15 seconds, it'll be at the top. Another 15 seconds, it'll be at point C. Another 15 seconds, it'll be at the bottom. And another 15 seconds, it completes that period a second time. Oops, I used the word period to kind of clue you in on something there. And so do we see the patterns, right? It goes up, down, up, down. Yes, seems periodic, right? So what is the period? I'll pause, let you answer. If you said 60 seconds, you would be correct. So again, we're going to bring all this back, all the vocabulary we've been working on, amplitude, period, shifting, up, down, left, right. We're going to look at all those pieces. So let's go ahead and plot these points. So x comma y. From that table up above, hit pause and plot them in your book as well here on page 542. All right, I'll plot them as well, and you can compare against your graph. And oh my goodness gracious, there it is. It looks a lot like our sine and cosine graphs that we've been seeing along the way in our previous section. So yes, the height of you, as you ride on this Ferris wheel, goes up and up and down over and over and over again. So it's at 56. It has a max of 100 and a minimum of 12. And so let's start to kind of analyze these things. So what's the amplitude? So the amplitude, again, is how much it goes up and down from this midline. If we bring that back, right? So this would be 44 and 44 up and down. So 44 feet is our amplitude, or our A value. The midline is just that horizontal line at y equals 56, right? And so really what that is our shift up, right? So it's been shifted up, or plus k, or plus 56 when we're thinking about our equation here. So how do we write an equation for this if we know what the amplitude is, we know what the period is, and we know what its shift up is? If you notice, it has not been shifted left or right. If you consider that we start at kind of the midline, kind of that zero value, we end at the zero, the middle, the quarter is the max, the 3/4 is the min. So if I'm thinking about that as my general sign pattern, if I'm thinking about that as my general sign of X pattern, there is no left-right shift, just an upshift, an amplitude change, and a period change. So we can kind of work backwards from that to figure out an actual equation to model the Ferris wheel height. Pretty cool. So again, from our word wall, we want to make note of this generic sine equation that we can modify based on the amplitude, the period, the left-right shift, or the up-down shift. So a couple of things to note, like we saw in our observation. So h is going to be equal to 0. There is no left-right shift. Okay, that's pretty easy. Our a is equal to 44, as we already said, and our k is equal to 56, because we've been, plus 56, we moved up 56. But what about our b? So b is related to the period of the function, right? And so we have this formula that 2 pi over b equals our period. Okay, so we know our period, though. Our period is 60 seconds. So how can we relate this? So 2 pi over b equals 60, and I've got to solve it for b. So basically, I'm going to multiply both sides by b and get 2 pi equals 60 times b. How do I get b by itself? I divide by 60. So I get 2 pi divided by 60 equals b. And then if I simplify that, that's really pi over 30 equals b. So even though that's a weird number, it still can be used to create my equation here. So what is the height? F of t equals a. We know our a is 44. That's our radius of our Ferris wheel, or half the diameter. And then times the sine of b, which in this case is pi over 30. 2 pi divided by pi over 30 will give us 60. And then x minus h, there is no h here because there's no left-right shift. And then plus k, that's on the outside, the plus 56 feet in the air. And there we go. Okay, so we can check if this is reasonable by graphing on Desmos or other graphing calculator. We'll make sure that our range is good. So I'll go ahead and graph that on Desmos if you want to as well, and then I'll take a picture and put it here into the notes. Okay, let's take a look at our graph here. I typed what we had put out here. It should have been variable t, I'm sorry, up here. But when we go to put it in our calculator, using y and x is okay. And I pointed out some maxes and mins along the way, as long as that y-intercept. So again, it hits the same values we saw in our table to make it reasonable. And then how's it compared to the graph of sine? Well, it's been shifted up 56. The period has been changed. In this case, it's actually been expanded, right, stretched out. And the amplitude has been vertically stretched as well as we look at those. Reasonable domain, obviously, the t value, we're really only worried about t being bigger than 0, but we also probably want to limit it to whatever the ride length is. So let's assume that's 120 seconds. So t being between 120 and 0 is probably good. And so then its range, obviously, is, the lowest you can go versus the highest you can go in terms of that height. So 100 feet at the max, 12 feet at the lowest. For the range, or y being limited between 12 and 100. So again, what's cool is we can now have a function, so we can actually plug values in using the calculator to find out what is f of 20. So first of all, f of 20 is the height of the car, right? The car on the Ferris wheel, height of the car at 20 seconds. And we're going to go ahead and just type that into our calculator here real quick, and I'll show you what that answer was to the nearest tenth. Okay, so a couple of quick notes here. You'll want to double check that both your graphing calculator and when you go to evaluate it, make sure it was in radian mode if it wasn't already. If you weren't in radian mode, if you were in degree mode, you would have gotten 57, which is an incorrect answer because it thought it was 20 degrees, not 20 radians. So again, you need to make sure that when we're doing all the stuff for this section, it's all going to be in radians. So radian mode, there we go, 94 up to 20. Think about it, 15 seconds I'm at the peak, and then I'm starting to come back down, so I'm 6 feet lower. That makes sense. So 94.1 feet. And again, that makes sense from, if I look at 20 here on my graph, it's in the 90s up there. So again, make that connection from here up to here graphically, and just visually on the picture, it makes sense. I got past the peak in 15, and then I'm coming back down. So after 20 seconds, the height of the car is 94.1 feet. So again, let's fully analyze these situations. I really like this. During the first two complete rotations of the sky wheel, give the times when the car is moving upward or downward. Remember that if I'm looking at this, I'm starting here and I'm rotating that way. So I'm moving upward during those first 15 seconds. So 0 to 15 seconds, I'm moving upward. And then from 15 seconds down, let's see, that's going to take 15 and 15, so that's going to be 45. So from 15 to 45 seconds, I'm moving downwards. And then I'm going to have another 30 seconds of moving upwards. So, and I'm only going through two rotations. So this is the first and into the second. So now I'm moving upwards from 45 to 75 seconds when I get back up here. And you can look back at the tables for these values too. And then another 30 seconds coming down. So then from 75 to 105 seconds, I'm moving downwards. And then the last 15 seconds from 105 to 120, that's when I'm moving upward again on that last little part before I get back to where I started. So all of this, remember, was because I started with a car that was already at that 56-foot mark, which made it very easy to write my sine graph. If I'd started with a different starting position, that might change the left-right shift of my graph. So you'll have to keep that in mind as you analyze new situations. So the Skywheel will be a part of an amusement park that has several pine trees that are 80 feet tall. Tyrell wants to know the times in the car will be above the height of the tree tops. So we're going to write an equation that Tyrell can solve to find the times. So obviously we're interested in the height. The height is our function. So remember f of t is equal to 44 times the sine of pi over 30 times x, or t actually, plus 56. And I'm wondering when that height is going to be 80. So when does it equal 80? Well, I'm going to graph both of these. I already have one graphed, and then I can graph the other one. And are there ways to solve this by hand without using a calculator? Yes, but you and I both know if we graph the left, graph the right, see where they intersect, it's so much easier. And especially with something that repeats, you're going to have multiple answers over and over again. So we're going to graph y equals 80 as well as our original function. I'll paste the picture in here of the intersection points. If you use your TI-84, you can do second calc intersect, but again, the Desmos calculator is super helpful here as well. So try that, see where they intersect. So there you go. We see that the height is above 80 at these different marks, or hits 80, and then it's going to be above between those. So again, use your calculator to find the times when the height is during the first two complete rotations. So I cut it off at 120. It'll keep hitting it over and over. But again, I wanted to find how many times. So it actually does this twice. Once going up, once going down, and then again on the second rotation, going up and going down. Again. So when will it be above the treetops? So the first interval is from 5.5 to 24.5 seconds. It'll be above the treetops. And again, so it was this one. And then again at 65.5. 60 seconds later, that's the period, to 84.5 seconds is when it will be above the treetops. When is it at exactly 80? At all four of those particular ones rounded to the nearest tenth. Okay. So now we're going to switch colors and we're going to see how we modify this function a little bit. So now we want to write a new function, g of t, that models the function of the car starting at the bottom, point D. So let's draw a quick picture here. Okay, here's our Ferris wheel. I'm going to be at point D. So this is at the bottom. So remember at 0 seconds, it's at a height, g of t, equaling to 12. Okay, So let's think about this, all right? It's gonna have the same amplitude, the same period, but let's actually draw the graph first. So here's my time, here's my height. So times equals 0, it's at 12, so it's actually starting at the bottom. And then after 15 seconds, it'll be up to that 56 point. After 15 more seconds, it'll be up to that maximum point. After 15 more seconds, it'll be back to 56 and then back at 12. So let's draw these so far, and then we can draw a few more in there if we want to. So 0, 12. Okay, so hopefully you tried that on your own. I kind of made my own table again, thinking about this car motion starting at 12 and then going up. So it hits those same values, just off a little bit from the times that we saw before. So the shape is the same as what we saw in our previous function, but just shifted. So if I'm still using sine, you could use cosine if you really wanted to, but if I'm still using sine, I have to think about the start, end, mid, and the quarters here. So really, in my mind, the amplitude of 44 is the same. The period of 60, so b equaling pi over 30, is the same. The shift up of 56 is the same, but now I've been actually shifted right. How much? I've been shifted right, that's at 15 seconds. So really, that's all I would need to do. So my function, f of t, or sorry, not f of t now this time, g of t, is almost going to be exactly the same. 44 times the sine of pi over 30, parentheses, and instead of x by itself, it's going to be x minus 15, because to the right is minus 15, and then plus 56 outside of that. So 44 times the sine, pi over 30, x minus 15, plus 56. This is not the only way to write this function. You could actually write it with a cosine. So there's a little bit extra challenge to you if you wanted to write it with a cosine. I'll reveal that in 5 seconds if you want to try it yourself. Okay, if you wanted to write it with cosine, I'm actually starting down here at the minimum, so it would be a negative, ending at the maximum. The period is the same, kind of, if you think about it. So the amplitude would still be 44. Cosine starts at a maximum there, so there's no left-right shift. I'm just going to make it a negative 44, so it's starting at the minimum, at the down part, because it's been reflected, pi over 30, x, because there's no left-right shift, and then the plus 56. So if you graph both of those, they'll actually give you the exact same graph if you tested it on Desmos or your TI-84. But for now, we're going to focus on really just using sine and thinking about that starting at the midline piece, but you could use cosine as well. So just a clever way. So we've kind of talked about how they're similar already. Number 18, what would have to be changed if the sky would be at 102 feet tall rather than 100 feet? The highest point of the sky wheel. So let's assume that we're keeping the same 88-foot diameter, so 44 feet. So I just got to move the whole thing up 2 more feet, right? So the midline would be at 58 feet then. To reach that, the 44 plus the 58. So at that point, the plus 56 would change to plus 58 would be the only thing that would change at that point. So now we're going to look at a couple of sky wheels. Again, we can represent this with a graph, table, equation, and move well through each, and how to pull information from anyone. So we're comparing the sky wheel to 2 other Ferris wheels, the round robin and the spin cycle. So which of these, so we already know from the sky wheel, its period was equal to 60 seconds. So now it asks us which of the 3 Ferris wheels, the sky wheel, round robin, or spin cycle, rotates fastest. So this period was 60 seconds. Looking at the table here, so starting at 8 and getting back to 8, that's going to be my period there. Not for the 45. The 45 is going to wind up being my midline. So I'm really looking at minimum to minimum. So 12 to 60 would be a full cycle there, 0 to 48. This tells me my period is 48 seconds for the round robin. And here, remember, our period is 2 pi over b for the spin cycle, so that's 2 pi divided by pi over 45, which becomes 2 pi times 45 over pi. So that's 2 times 45, or 90 seconds for its period. So which one's rotating fastest? 1 revolution per 60, per 48, per 90. Round robin. Round robin has the shortest period, so it is spinning the fastest. Makes 1 revolution every 48 seconds. A little bit more interesting now. What's the tallest? So this is kind of looking at our max value. Our max value is always going to be that midline value. plus the amplitude. So if I'm thinking about that in blue, for the sky wheel, we already saw that that was our 44 plus our 56. That was 100 feet tall for the sky wheel. What's our height here? Our max height is 82 feet. And here, since it's in that equation, I've got to do that midline of 43 plus the amplitude of 33. That's going to hit a maximum of 76 feet. Okay, so 76, 82, and 100. Pretty obviously, the sky wheel is tallest at 100 feet. And again, we're going through this exercise just so you can see there's different ways of getting the same information out from a table, an equation, or a graph. So again, that 100 feet, we saw that as the peak, the top of that trig graph as we graphed it. And which of the three Ferris wheels has the greatest diameter? So again, the amplitude is equal to the diameter divided by 2. So we already saw for the sky wheel that was the 88 feet, right? So 44 feet for the amplitude, 88 feet for the diameter. This over here in the round robin has a low of 8 and a high of 82. So that tells me 82 minus 8 is going to give me a 74-foot diameter. And its amplitude then, if I divide that by 2, would actually be 38 feet. No, 37 feet. 37 feet for the amplitude. And so 74 feet for the round robin. And here my amplitude is 33. So my diameter is 66 feet. So again, sky wheel at 88 feet has the biggest diameter, looking at all those different pieces there. So again, your job on the homework will be to look at where does my amplitude come from, how can I put that into my equation, and then analyze it. On 22, explain how you can determine the height of the car on the round robin after 4 minutes. So how many periods here? So 0 seconds, so 4 minutes is equal to 4 times 60, or 240 seconds. So how many of my 48-second periods is that? Well, 240 divided by 48 is 5. So this is 5 cycles. It's going to do 5 full cycles after starting out at 8 feet. But if it starts out there, it's going to end there. So since I'm ending on a whole cycle, it's going to be at 8 feet. It's going to still be there. If I was a quarter cycle in or a half cycle, we can figure out if it's, all the way at the top of the Ferris wheel or different things like that. And again, given the trig equation that models the motion of a Ferris wheel, how can you determine the diameter? The diameter, of course, is equal to double the amplitude, because the amplitude is half the diameter, so working in opposite ways. And that brings a conclusion to modeling real-world phenomena with the trig function. So give it a try in the worksheet in the multiple choice, kind of working backwards with your amplitudes, your shifts, your periods. I'll be there for office hours. Can't wait to see you this week, whether it's on this or later on Thursday when you're working through our last at-home test together. But thank you for a great year. I can't wait to see you all again in the fall, and hopefully you'll stop in this week to say hi and to have a great summer. I'll show you the word walls in the next couple of pages for a few seconds, and then I'll make sure to upload those as PDFs ahead of Thursday's test as well. Okay, here's page 1 of the word wall. Go ahead and pause here to write that down if you need to. And again, page 2, dealing with all of our shifts or transformations that are possible. A for the amplitude, B for the period change, the H and K, up, down for the K value, left, right for the H value, based on whichever generic shape you're looking at. Sine and cosine have some similarities. Tangent is kind of its unique thing. We really only do applications with sine, mostly cosine if needed, but mostly we can always write it in terms of sine. So I hope that this has been helpful, and let me know what I can do to help. Have a great day.